Great. So thank you everyone for coming today. I'm excited to introduce Johannes Carmesin, who will be talking about matroids and embedding graphs and surfaces.
Yeah, hello everyone. So I'm going to talk about some new method how matroids can be used to embed graphs and surfaces. So let me start by stating the problem. So a surface is a compact two-dimensional manifold without boundary. So for example, if you take, for example, the two-dimensional sphere is a surface. And if you take out one point, an arbitrary point from the two-dimensional sphere, you get the two-dimensional plane. Or a torus is a surface, or the Klein bottle, or just the torus and you stick on a bunch of handles. And now the question is, you're now given a graph and you want to embed it in a surface such that the vertices are embedded as points and the edges are embedded as some one-dimensional topological curves so that edges do not cross. And here you see an embedding of the red graph in the torus. And there are two main lines of research. So the first is what I call the specific embedding problem. And that is you fix a surface, for example, the torus, and now you decide which graphs embed into that surface. And the class of graphs embeddable on a fixed surface is closed undertaking minus. So by the Robertson and Seymour theorem, there's a finite list of excluded minus characterizing embeddability. So there's a polynomial time algorithm. And the algorithmic aspect of this problem was solved by Moha, who proved that actually there's a linear time algorithm for the specific embedding problem. And the other line of research is what I call the general embedding problem. So there you're just given a graph, but the surface is not fixed yet. And you're allowed to choose the surface in such a way that it fits best to the graph. So there the problem is you're given a graph and you want to, and yeah, of course, for every graph, there always is some surface so that the graph embeds into the surface. And here the task is you're given a graph and you want to find an optimal surface so that the graph embeds into that surface in an optimal way. And yeah, and in this talk we are concerned with the general embedding problem. And up to now, people have mostly thought about optimal way as meaning minimal genus. So what is this? So by the classification theorem of surfaces, every surface can be built from the two-dimensional sphere by adding a finite set of handles and by adding at most one Möbius strip. And now the genus of a surface is twice the number of handles you need to add, plus one if you needed a Möbius strip. Right, so this is some quantity that in some sense measures the complexity of the surface. And then what people are interested in is embedding graphs into surfaces of minimum genus. However, in 1989, Carmesin proved that the general embedding problem for surfaces is NP-hard. So there isn't any way how we can find an efficient algorithm that checks for a specific graph and constructs a surface of minimum genus, such as the graph embeds into that surface. Right, so very, very different. So for the specific problem, there's a linear time algorithm, and for the problem where the surface isn't specified, it's NP-hard. And what I'd like to suggest is the following. So I'd like to suggest that we replace the global minimum optimality criterion of minimum genus by a local condition. And this will have a drastic change on the complexity of the problem. Namely, it will change from NP-hard to polynomial. And the main tool to do this are matroids. Yet I'm sure you all know this. Yeah, but still, kind of let me start at the beginning of matroid theory. Right, so we're given some graph embedded in the plane. So for example, here you have the black graph that is embedded in the plane. And then we have a dual graph, which you get by putting a vertex into each face. So put a red vertex into each face. And now we join two of these faces if they share an edge. And this is a unique construction. For every black graph embedded in the plane or in the two-dimensional sphere, it's just the same, you always have a uniquely defined dual graph. And now Whitney had this amazing idea. He was interested in embedding graphs in the plane. And he had this idea that he didn't want to construct the embedding directly, but instead he first constructed this red dual graph without knowing the embedding in advance, and then used that red dual graph to actually construct that embedding. And by trying to construct the red graph directly from the black graph, he incidentally invented Matroids. And now in modern terms, this theorem of Whitney says the following from 1932, that a graph is planar, so it can be embedded in the plane, if and only if its dual matrix is graphic. Right, in this case, this dual matrix is just given by a binary matrix, and you just check whether there's a graph whose cycle matrix is given by that matrix. Right, so it's a very simple, very easy to check criterion, and this is also a very pleasing planarity criterion in the following way, namely it does not only tell you, it does not only tell you whether the graph is planar, but it also tells you how the possible embeddings look like. Because every possible embedding is essentially given by a dual graph. And the possible dual graphs are precisely the different graphs that have the same cycle matrix. So by this theorem, it's not only just telling you whether the graph is planar, but also how the embeddings look like. So this, somehow kind of the matrix really kind of answers the problem. Right, and so the question is, can we also do something similar for surfaces? Right, so how would that work? So we're interested in embedding the red graph into some surface, but we don't know the surface yet. So probably constructing the embedding directly would be so complicated, so we'd first like to compute some dual graph for the embedding. And constructing the dual graph is too complicated, so we'd rather find it as a given by some matroid, so as being the cycle matroid. Yes, the graph being given by some graphic matroid. And yeah, and then this graphic matroid we would compute as some surface dual matroid of a graph, and it's not really clear what this is now at this point in the talk. So let's be a bit more concrete. So how would this procedure work? So you start with an arbitrary abstract graph with no topological information at all. And then from this graph, you would compute some matrix, say some binary matrix. And yeah, and this is kind of part of the problem, how one could kind of find a good way how to compute that matrix. And then from that matrix, one would construct another graph, which we call the green graph. And this construction from the matrix to the graph should be really straightforward. Namely, it should be such that, you want that this would be a graphic matroid, and then the green graph would just be some graph such that its cycle matroid is represented by this matrix. Right, and now we could use this green graph to construct an embedding. How would that work? Well, if everything works out fine, then every vertex of the green graph will be a cycle in the red graph. More precisely, for every vertex over here, the outgoing edges, there would be a bijection between the edges in the green graph and the edges in the red graph. And so if you look at a vertex, the outgoing edges, they would form a cycle in the red graph. For example, these three edges going out here, they would form this cycle in the red graph. And now for every vertex, its outgoing edges would be a cycle in the other graph, so you would attach a disk onto that cycle. And you would do that for every vertex of the green graph. And because every edge of the green graph has two end vertices, for every edge of the red graph, you would attach two disks. So locally at the disks, this really would be planar. And if we figure this out for this example, this is what you get. So this is just another way to draw the red graph. And right, so this is also, I mean, this is now a planar model for the torus, right? You identify the left and the right and the top and the bottom. So if you know for every vertex of the green graph, attach a disk on a cycle of the red graph, then if you kind of put these all together, what you're going to get is a torus, and you would get a simultaneous embedding of the red graph and the green graph in the torus. Right, but why is now the time to do that? I mean, Whitney's theorem is around for quite some time, and people have known this theorem quite well. So why is now the right time to actually extend Whitney's theorem to surfaces? Well, actually, there recently has been some progress in this direction. And yeah, I mean, this slide won't matter for the rest of the talk at all. It's just kind of for people who kind of know these things to connect things. And the two-dimensional simplicial complex is just a graph where you put some disks onto some triangles of that graph. So it's then a two-dimensional object. And this theorem says that a simply connected two-dimensional simplicial complex satisfying some necessary condition, which I won't talk about today. So this simply connected two complex can be embedded in three-dimensional space so that the faces do not cross, if and only if some associated matroid is graphic. So this is really like in Whitney's theorem, right? You have an embedding if and only if some associated matroid is graphic. And in the remainder of this talk, this is what I will call a Whitney type theorem. So this would be some equivalence between the existence of some embedding to a certain matroid being graphic. This would be what I call Whitney theorem. Right, and so now what can we do? So this is the main definition of the talk, and it's as follows. So you're given a parameter R, and we say that an embedding of a graph G in a surface S is R locally planar, so locally planar with parameter R, if every cycle of G of length at most R is generated by the phase boundaries. I mean, this might perhaps sound a bit kind of complicated definition of what locally planar means. So perhaps, and this is essentially the same as the following perhaps more graph theoretic definition, which says if you take a vertex and you take the ball of radius R around that vertex and you restrict the embedding to that ball, then this would be a planar embedding. But I mean, it's not totally equivalent, but morally it's basically the same. But actually, in this talk, we'd like to work with matroids, and so it's much more natural to state everything in terms of cycles than instead of vertices. And actually, with this definition, everything in this talk goes through. And just to quickly check that it makes sense, so if you let the parameter R go to infinity, then actually this specializes just to planar embeddings. So in this sense, this is a generalization of planar embeddings. And the idea to use local planarity as a tool was introduced by Robson and Seymour in the Graph Minus project. And there's some other related paper of Carmesin from 1990, which I believe was far ahead of its time. So what he proved there is that if you take a particular type of locally planar embeddings, namely those where every phase boundary is short, then actually he proved that such locally planar embeddings with this additional property are always of minimum genus. And he also found a polynomial algorithm to check whether a graph has these embeddings. And yeah, nowadays, locally planar embeddings are used in quite a few places. And corresponding to the notion of locally planar embedding, we also have an associated matroid. And this matroid is really just like the cycle matrix of a graph, but you just consider the bounded length cycles. Right, so let me be more explicit. So again, you're just given some parameter r, and now you say that define the r-local matroid of that graph to be the matroid whose circuits are obtained in the following way. So you look what the circuits of bounded lengths generate, and now you take the minimal non-empty subsets of this. Or put another way, perhaps think about this as being a binary matroid, and then you just have to specify the circuit space of that binary matroid. And this is just a space generated over F2 by the circuits of bounded lengths, the circuits of lengths at most r. And again, if r is equal to infinity, then this is just the usual cycle matroid. But for smaller values of r, there are some large cycles that may be ignored. I mean, they may be generated by the short cycles, or they may be not.
Just to be clear, when you say generated, this is something that builds binary matroids and nothing else. Is that right?
Yes.
Okay.
At the very end, there's also, perhaps a good point to say now. Everything I'm saying until the last 2 or 3 minutes of the talk will just be, everything will be binary, but you could also work with ternary matroids instead. So when you take everything over F3. And then it will no longer be about embeddings in general surfaces, but embeddings in orientable surfaces. Yeah, thank you very much. Excellent comment. Right, but for now, let everything be binary. And yeah, so whenever I say generate, it's always binary. Yeah, and this is the main term of the talk. So which says the following: you're given a parameter r, and then an r locally 2 connected graph. And yeah, please for now ignore this assumption of r locally 2 connected. On the next slide, I will tell why it's not important, or why you can kind of generalize beyond this condition. But for now, let's just have it here, just to keep things simpler. Right, so you have now graph G, and then it has an r locally planar embedding in a surface if and only if its r local matroid is co-graphic. So this is really Whitney type statement, because the existence of an r locally planar embedding is equivalent to a certain matroid, the r local matroid being co-graphic. Yeah, note that this is a characterization, right? So if you're now interested in building an r locally planar embedding, then you look at the matroid, and then the matroid will be graphic, and actually this graph given by the matroid will actually help you constructing the embedding, and it will be something like the dual graph of the embedding. And on the other hand, if there doesn't exist an r locally planar embedding, there's a simple certificate for this, namely this matroid is not graphic, and this is the only way how this can go wrong. So this really means that the answer to this question is completely matroidal, right? The matroid completely gives the answer to this embedding problem. And like in Whitney's theorem, right? So it's not only about the existence of embedding, but this theorem kind of goes a step further, right? It also gives us an overview about the possibilities of these locally planar embeddings, because essentially these locally planar embeddings specify to know how they look like, you just need to specify a dual graph, essentially. And this dual graph will then be we will able to compute this dual graph from this dual matroid. Yeah, now coming back to this question we had at the beginning, and now what we could, right, so there's this general embedding problem, right? The problem, you're given graph, what is the best surface to embed this graph in? And before it was, we thought about, we wanted to construct a surface of minimum genus so that the graph embeds into that surface. But in view of this theorem, what also might be natural is to say, perhaps we want to have this more local optimality criterion, right? So replace the criterion of minimum genus by the criterion having maximal local planarity. And this has a drastic change in complexity, right? Before the problem was NP-hard, and now it's polynomial. Because computing this R local matroid can be done in polynomial time, and they're just polynomial linearly many values for R where you have to check it. So now there is a polynomial algorithm for this modified embedding problem. And by this paper of Carmesin, which I mentioned earlier, where so first, by this difference in complexity, it cannot be true that every maximally locally planar embedding can have minimum genus. But Carmesin proved that if in a maximally locally planar embedding all the phase boundaries are short, then actually this must be of minimum genus. Right. So now I promise to talk about this condition of local two-connectedness. Right. So what is a local cut vertex? So you say that a vertex is a local cut vertex if you take the ball of with parameter r, if you take the ball of radius r around that vertex, and you remove that vertex from the ball, and this disconnects the ball. This is what you call a local cut vertex. And now a graph is locally two-connected if it doesn't have a local cut vertex. So whenever you take a vertex, an arbitrary vertex, and you take a ball of radius r around that vertex and remove that vertex from the ball, then the ball would still be connected. Right, so how do we extend the theorem to graphs that need not be locally two-connected? Well, if you have an arbitrary graph that may have some local cut vertices here and there, then at these local cut vertices, you could split the graph locally, which gives you a locally two-connected graph. Then you apply the theorem, and then you glue back together these local cut vertices. And I believe that this is most naturally formulated in terms of pseudosurfaces. So a pseudosurface you get from a genuine surface by just identifying finitely many points. So for example, in this picture, we started with the torus and identified 2 points of the torus. And this is a pseudosurface obtained by the torus by identifying these 2 points. And of course, every surface is a pseudosurface. But on the other hand, if you have an embedding of a graph in a pseudosurface, you could always kind of make some small modifications here, add some tube from left to right to make this an embedding into an actual surface. So yeah, that's essentially the same. And then, this sketch I was just giving about how kind of to extend the embedding, then just easily gives the following theorem as a corollary of the main result. So you're given a parameter r, then a graph has an r locally planar embedding in a pseudosurface if and only if its r local major is co-graphic. So this is really like the other theorem we had before, but without this assumption of local two-connectedness. But you have to consider these embeddings into these more general surfaces. Right, so and this and yeah, this slide also won't matter for the rest of the talk, but I thought it's kind of nice to talk a little bit about kind of how I came up with this idea to think about this Whitney theorem. So when you look at the proof of Kuratowski's theorem or at Whitney's theorem, three connected graphs kind of appear naturally in the following sense. So it seems like the core of the proof is kind of a three connected case, because if you just prove Kuratowski's theorem for three connected graphs, then kind of all these topological difficulties just disappear, and you can quite straightforward can just kind of prove the thing. And then you use this decomposition theory to actually get it from three connected graphs to general graphs. So kind of the concept of three connected graphs kind of naturally appears in the proof of Kuratowski's theorem, and kind of gives and also kind of three connected graphs have unique embeddings and so on. So I think they're kind of really helpful tool to understand embeddings in the plane. And I believe that, in some sense, I think the connection between embeddings in the plane and connectivity is similar to embeddings in surfaces, the relation of embeddings in surfaces and local connectivity. I mean, we already see in the statement of the main result that kind of local connectivity is kind of important, and also later in the proof, this will kind of appear in a key step, which is kind of somewhat similar to this other thing. And it's already an exciting question, what are local separators of graphs? I mean, for local one separators, we just saw what they are, but I mean, if you look at higher sets of vertices, when do they form a local separator? And this is a non-trivial question because the following doesn't work. So you could say, I mean, here's a naive definition which is not correct. You say that a set of vertices is a local separator if whenever you take a ball around that vertex set, then it would separate that ball. And this is not a good definition because if you take that definition, there are some graphs where these objects do not satisfy the corner property, which is some property genuine separators have, which is related to submodularity and is the reason why kind of separators have many nice properties. But actually what you can do is but actually there is a definition of local separators, and this is completely oversimplifying, but roughly it goes like this. So you say that a set of vertices is a local separator if you can take a ball around them, but this ball gets more fuzzy towards the boundary and with the right amount of fuzziness so that it actually has the submodularity property. Right, so there are now these local separators and they behave very similar to genuine separators. And that is the reason why now you can extend many theorems about graphs with separators to extend to local separators. For example, the notion of a tree decomposition now extends to the notion of a graph decomposition, which is just the same thing, but where you replace the decomposition tree in a tree decomposition by a general graph. And then if you take a long cycle, before in the theory, this was always treated as a graph of tree with 2, and now it would be treated as a graph of cycle with 1. And it seems to be that now we have like this more detailed language. So for example, for classes of graphs of bounded tree widths, perhaps you could improve various constants using these ideas. And there are also many other open problems in that area. Right, so now back to the main part of the talk. Right, so now I'd like to talk about the proof of the main theorem. So remember that we wanted to prove we're given a locally two-connected graph G, and we wanted to prove that it has a locally planar embedding if and only if this local matroid was co-graphic. And the way I present the proof is that we deduce this Whitney-type theorem from this more general version, from this more abstract version. Right, so what is this version saying? So G is just some two-connected graph, and S is a non-empty subspace of its cycle space over F2. And the only way we're going to apply this theorem will be when S is the circuit space of this local matroid, this R local matroid we defined earlier. So S is the set generated by the bounded cycles. That's the only way we're going to apply this. And it has a cyclic generating set. And now assume that S is locally connected and fencing in. All right, so there are various assumptions in that theorem. Please ignore them for a while because I won't define them in the talk. The only non-trivial condition is this fencing in we have here. And yeah, I mean, this is a non-trivial condition. And actually, I will present it in such a way that later on in the proof, this will turn out as the natural thing we want to have. So please bear with me. I won't define it yet, but I will define it later in the proof when it's clear kind of why we need some condition like this. And then the conclusion is really what we want to have, right? Then G has an S facial embedding, which for our local matroids will just specify to an R locally planar embedding into a surface if and only if the R local matroid, the S local matroid, which is specialized to the R local matroid, is co-graphic. Right? The conclusion is really just what we want to have. you have this locally planar embedding if and only if the matrix is co-graphic. And the assumptions of this more abstract version, so they're kind of in this more general setting where you're allowed an arbitrary vector space S, but the price you'll have to pay that you have to check this additional assumption of fencing in. Right, so let me talk about the proof of this abstract duality theorem. Right, so first implication. So assume that this associated matroid for the graph G is co-graphic. Well, if it's co-graphic, then there must be some graph associated to this. Right, so there's a graph H, such that if you look at the cycle matroid of the graph H, and then this is the dual to this matroid. And this graph H will be the candidate for the dual graph of the embedding. And then the next thing you prove is that the vertices of the graph G are cycles in the graph H. So why should that be true? If you take a vertex and all the outgoing edges, then this would be a bond in the graph, right? So it's orthogonal to all the cycles in the graph H. And the set S is a subset of these cycles. And then you can use this local connectivity assumption to actually show that the vertices, so let me say again. So the vertices of the graph G, right, if you take the outgoing edges, so this would be an atomic bond of the graph G, this would be orthogonal to all the cycles of the graph G. And now S is a subset of all these cycles, so in particular it will be orthogonal to all the elements in S. And now the local connectivity assumption gives you that these vertices are really minimal. So these atomic cuts at the vertices are minimal elements that are orthogonal to all cycles of G, and these are then precisely the cycles in the graph H. It takes a page or so to prove this, but you get the idea. Right, so now let's assume that we have this, that the vertices of the graph G correspond to the cycles of the graph H. Okay, so with this now we could start constructing embedding. How? We would start with the graph, with the geometric realization of the graph H, right, which would just be a one-dimensional simplicial complex with the edges being some one-dimensional intervals. And now for every vertex of the graph G, we would now attach a disk onto its corresponding cycle in the graph H. And again, as before, we have some bijection. Just from the construction, we have a bijection between the edges of G and the edges of H. Right, so now at every edge of the graph H, its corresponding H in the graph G is in two vertices. So at this edge, you would have two disks attaching at that edge. So at interior points of edges, that would be locally two-dimensional. So what happens at vertices of the graph H? There you don't quite get that it's two-dimensional, because what could happen is that you have two planes, or an arbitrary number of planes, intersecting in a point. So you get a simultaneous, right. So you get that this object you're going to get is not a surface, but it's a pseudo-surface. So it's two-dimensional at every point, except for these, the vertices of H, there may be kind of several planes locally kind of intersecting at a point. So it's a pseudo-surface. And the singularities of the pseudo-surface, so these non-two-dimensional points, are all vertices of the graph H. And actually, we also get an embedding of the graph G into that surface. How? Every vertex of the graph G is in the middle of some disk we attached, and then we just kind of embed all the vertices in the midpoint, as the midpoints of these disks, and just join them by some edges, going through the corresponding edges of H. So what we get is a simultaneous embedding of the graph G and H in a pseudo-surface. Right, and now we just have to do some minor surgery to actually transform that into an embedding of G in a genuine surface. How do we do this? I mean, the only singularities of the pseudosurface are at vertices of H, and the only thing that can go wrong is that there are some disks around that point it just glued together at a single point. So you just kind of disconnect them at the single point. So perhaps just remove these single points and then take the completion. And this way, and because this is only changes things at the vertices of H, the embedding of the graph G is not changed, and you get an embedding of the graph G in a genuine surface. Right, so let's summarize. How does this first implication go? So you start with a matroid being co-graphic. From this, you build a graph H that serves as the candidate for the dual graph of the embedding. Then, for every vertex of the graph G, you glue some disks onto the graph H, which gives you a pseudo-surface in which the graphs G and H embed simultaneously, and then you do some minor surgery to get an embedding, transform this into a surface, so that the graph G embeds into that surface. Right, so let's talk about the second implication. So here now you start with the graph G embedded locally planarly in some surface. And now the graph H will then just be the dual graph of the embedding, right? So you put a vertex into each face of the embedding, and if two faces share an edge, you put an edge in the dual graph H. And if all face boundaries are short, then it's fairly easy to see that if you take the cycle matroid of the graph H, this is equal to the dual matroid of the graph G. However, in general, it need not always be the case that all face boundaries are short. I mean, why should they be? Right, so to explain how we deal with the other case, let's first go a step back and reflect on the statement of the main theorem. So in Whitney's original theorem, the graph represented by the matroid was always equal to the dual graph of the embedding. However, in our theorem, it will be that the graph represented by the matroid will only be equal to a quotient of the dual graph of the embedding. And here I say that if you start with a big graph, and then taking a quotient just means identify arbitrary vertices, right? So you say that a small graph is a quotient of a big graph if you can get the small graph from the big graph by identifying some vertices. And we already saw that phenomenon arising in the first direction of the proof, right? So you remember that we had the simultaneous embedding of the graph H and the graph G into some pseudosurface. And now we had to detach the pseudosurface at all these singularity points, which were vertices of the graph H, right? So this is like the inverse operation of taking a quotient. Right, and now in the second implication, what we'll have to do is actually doing this quotient operation. So we have now this dual graph of the embedding, and we now have to find a suitable quotient that will be equal to this matroid. Yeah, and by the way, if all the face boundaries are short, then actually you have equality here, and that's why there's such an easy proof that these two things coincide. But in the general case, we now have to actually build our quotient. And this is precisely where this notion of fencing in comes in, because this will not always be possible to build that quotient, but there's some condition and that will ensure that it is. Right. Okay, so here's just embedding of some graph in a surface, just some kind of local piece of that embedding, and all face boundaries are short except for the three faces which are put in color. So there's the green face, the blue face, and the gray face, and these are the only long face boundaries. And Yeah, and I refer to these faces as holes. So the faces that have too large a boundary I call holes. And now, as usual, we denote by S sub r the set of cycles generated by cycles of bounded lengths. And this notion of fencing in, roughly speaking, means that now when you have a cycle, you could look how many holes are on the inside of that cycle. And you say that a cycle is smallest if the number of holes inside is minimal. And fencing in says that there exist some smallest cycles around holes. So if you take the cycle around a hole, every other smallest cycle either has precisely the same holes on the inside, or the set of holes on the inside are disjoint. For example, if there would be a cycle in SR containing the green hole and the blue hole, and there would be another short cycle containing the blue hole and the gray hole, by fencing in, there must also exist this short cycle just having the blue hole. And then you just prove that the set of SR, so the set of bounded cycles in which we're interested in, so the set of minimal non-empty things generated by the bounded cycles, this set is fencing in. Right, so let's summarize the very rough overview about the proof. So we don't prove the Whitney theorem for R locally planar embeddings directly, but we'll deduce it from a more general duality theorem. And this is just kind of the same formulation, except that we have this more abstract setting, and the non-trivial condition is this fencing in. Right, and when you are actually fencing in, I mean, so how does fencing in help you to build the quotient? I mean, if you have now one of these smallest cycles, there's a set of holes inside. And these holes, they will be vertices in the dual graph of the embedding. And how we build now this quotient is just to identify for every smallest cycle all the holes on the inside. And the notion of fencing in tells you precisely that this is a well-defined notion, because for any two smallest cycles, either they require the same identification or the interiors are disjoint, and so it's completely incomparable identifications. Yeah, so this notion of fencing in really tells you that you can nicely build this quotient, and that's roughly speaking why this other proof goes through then. All right, so if this notion of fencing in, and you have this more abstract theorem that has just this fencing in as the additional assumption, and then just prove that the set SR we are interested in is fencing in. And once you have all the ideas in place, this is probably technically the most complicated lemma in this paper. Right, so that's the rough overview of the proof. Right, so this we already mentioned briefly earlier. So far we worked always over the binary field F2. But you could work over any other field. And what's happened then is that you're no longer interested in embeddings in general surfaces, but you just get embeddings in orientable surfaces. Right, and this is just the same definition of R local matroid, but over F3. And then the theorem is for F3, you're given a parameter R, and R locally to connect graph G has an R locally planar embedding in an orientable surface if and only if its R local matroid over F3 is co-graphic. So again, a Whitney type theorem, embedding in orientable surface that's locally planar if and only if some matroid is co-graphic. So let's summarize. So 1989, Carmesin proved that the general embedding problem for minimum genus is NP-complete. And at that time, probably because people were not quite satisfied with this, they also suggested first we should look at subclasses of the graphs of all graphs. But for these subclasses, Carmesin was able to extend his construction. So for example, he proved that also, if you just look at bounded degree graphs, then the embedding problem for minimum genus is still NP-complete. And now we have this new Whitney type theorem for surfaces. So which roughly goes like this. You start with your arbitrary graph, you use this local matroid to build a dual graph, and then you use this dual graph to actually construct that embedding. And this gives us a characterization of embeddability in terms of these dual matroids being co-graphic. And now what I suppose is the following, that we take this notion of minimum genus, this optimality criterion of minimum genus, and replace it by this local optimality criterion of local maximum planarity. And if we modify the general embedding problem in this way, then there's a drastic change in complexity. Namely, it goes from NP-hard to polynomial. And as I mentioned earlier, not every, because of this difference in complexity, not every maximally locally planar embedding can be of minimum genus. But if all phase boundaries are short, then they are of minimum genus. Right, so open questions. Right, so in our proof we had this very general Whitney type theorem, and then for the specific set of circuits we were interested in, we proved that they were fencing in, and then we were able to apply this more abstract Whitney theorem. And our natural thing to try is why not do this for some other subspaces of the cyclospace? I mean, this fencing in properties, I don't know. It's wide guesses, of course, but it's perhaps it's similar to this in these theta properties in these quasi-graphic bits. I don't know. I mean, there are people here who know much more about these things than I do, but I think that would be very exciting, right? If we could prove some surface duality theorems for some other classes and subspaces of the cyclospace of a graph. And this would also connect with this pioneering work of Silati, who proved some theorems reminiscent of Whitney's theorem for the specific embedding problem for embeddings in the real projective plane and the torus. And yeah, I think it would be very exciting to kind of be able to kind of push that further, using the setup to kind of the general embedding problem. But yeah, I mean, it's wide guesses. I mean, I don't know how to do that, but I think I would be very interested in ideas here, or in kind of somebody kind of working on these type of things. Right, and then there's another question. I think also here's the right place to ask this. So before I talked about these local separators of graphs, and right, and there's a very natural notion of local two separators of graphs, and I was able to extend, right, so there's this Tat decomposition theorem, which decomposes every connected graph, every two connected graph into these three connected pieces, and this decomposition is essentially unique. And I think it would be very exciting, right? I extended this to this local version, giving a really precise definition, really precise version, so that all these pieces you have are locally three connected, or cycles of length at most r. And yeah, also it has kind of this uniqueness statement that this decomposition is unique, similar as this Tat decomposition for graphs. And I think it would be very exciting to have a majored analog of this, similar as Tat's decomposition for graph is also a majored analog. Yeah, so I'd like to organize some small open problems workshop related to this. And if you would be interested in an event like this, it would be great if you could send me an email. And also I have a postdoc position working on things related to this work. And actually it's quite a nice thing, so it's for up to 5 years. And if you would be interested, just check my webpage. And yeah, I mean, it was delayed due to all these COVID rules before, but now it's open. Yeah, so just check my webpage if you're interested in, yeah. And yeah, thank you very much for listening. And yeah, here are the open problems again.
Thank you, Johannes. I've found that it's hard to do applause after these things, so unfortunately I think we have to skip that, but thank you. Are there any questions? I'll give people a minute, but then I have one also. I guess quickly, first of all, if your graph is locally two connected, do you actually get these long facial cycles?
Sorry, say again?
If your graph is locally two connected, do you actually get the case that there are long facial cycles?
Yes, yes, you do. I mean, an easy way how you could do that is just you take something such that all facial cycles are short, and now you take some small disk and just put an arbitrary planar graph inside, which has some long cycles.
Gotcha.
Oh man, calling me out now. And this is very
Okay. So yeah, thanks for a nice talk. I wanted to check some things about this. Sorry, about this local planarity. So you had two different theorems with local planarity, and if I understood rightly, that means that the short cycles are generated out of the facial cycles. But one was in a binary context and one was in a ternary context. Does that mean that in those two contexts you have different meanings of local planarity?
Yes, yes.
Okay. And if I wanted to have a notion of generation where instead I say,
many years ago.
if I have two of the cycles of a theta, then I also have the third cycle of the theta, right? That kind of generation.
Yeah.
I mean, would there be some way to characterize that kind of local planarity in some surfaces? Or would that?
Primary objectives.
I mean, this is about this open question, right? So I don't know. Probably that's, I mean, perhaps you asked the question because something is more clearer to you than it is to me. So I think I have to say that I don't know. But I could mention that, I mean, in this notion of generation, somehow being binary is kind of built in. And kind of the reason why kind of for the ternary things, you just get orientable surfaces because they're automatically binary. And that kind of, for these, I mean, if you have a binary matrix that's ternary, it's automatically regular, right? So you get kind of the same answer for every non-binary field somehow. But I don't know, it probably doesn't have to do so much with your question.
It's like a hobby during the night, which we noted is probably something we shouldn't ramp up.
All right, I have another question, which is, do you know what you get if you apply the grid theorem to R local matroids?
No, I mean, that's like.
Wait, so I have plastic.
Like, I'm wondering if it relates to, yeah, if you plot, like, when do they have bounded branch depth? Like, you'd hope that it would be these bounded depth grid minors again, but that seems too optimistic to ask.
No, I think you would kind of have to have a new proof, right, to get these bounded depth grids somehow, I would think.
No.
Yeah, I don't know, but I think, I mean, what would be nice to have in this context would be some bounded depth grid theorem, right, to kind of fit nicely to these embedding things. And yeah, I mean, probably try to kind of build the whole theory with kind of these local separators. But there are lots of open questions there, and it's kind of not clear how to do any of them, right?
Right. All right, let me thank you again. I'll go ahead and turn off the recording.